Hello, this is Roger Cook, and I'm giving a little video on validation in expert judgment. We'll cover in-sample validation, out-of-sample validation, something called the random expert hypothesis, and the whole issue of prediction. Okay, so let's get started. Here we see 6 recent studies, starting on the upper left with the iSheet study that was published in PNAS in spring of 2019. For each study, we see 4 calibration variables taken from the expert's field. And for each calibration variable, we see for each expert in the study, his 5% and 95% values given as this interval, and the median given as this black dot. And we also see the true value given as this red line. So as you let your eye wander over this sheet, you can see all of the good and the bad and the ugly with expert judgment. So for example, if we look at the study GDP and oil here in the lower right, we see an example of an expert who is highly informative, but very inaccurate statistically. So you see here for this first variable, he thinks there's a 90% chance that the true value will be around 6, and it turns out to be about 32. So the probability of an event for him falling outside his 90% confidence band should be about 10%. It should happen once in a while. It shouldn't happen all of the time. And so here we see that in 4 out of 4 of these variables, his 90% confidence band misses the true value. Now, if that happens in 10 out of 10 variables, his statistical accuracy will be very low. Moving over here to IQ and earnings, we see an expert who is accurate statistically, but rather uninformative relative to the other experts in the panel. And if that's the best we've got, then we're happy with that. But we would really prefer to see Goldilocks up here, who has high statistical accuracy and high information. So in structured expert judgment, we have quantitative measures for informativeness and statistical accuracy. We use these to construct performance-weighted combinations of expert judgments. And in this video, we're going to show the various ways in which those performance-weighted combinations are validated. Okay, before going further, let's just take one more look at the overall data. This is data from 49 studies completed between 2006 and 2019. And we plot the most accurate expert statistically as these red dots up here, and the least accurate experts down here. So you see the most accurate experts have a p-value that is above 0.1 in about 2/3 of the cases, and for the rest it's generally above 1 times 10 to the minus 2, which is a reasonably charitable threshold at which we would reject the hypothesis that this person is statistically accurate. Sorry, a little bit of Dutch there. And so we compare that with the blue diamonds down here, whose statistical accuracy score is in the neighborhood of 10 to the minus 6, 10 to the minus 8, even all the way down to 10 to the minus 8. So the lesson from this chart is that there is a great deal of variability in experts' performance with respect to statistical accuracy. So in this chart, we discuss in-sample validation. So the experts have assessed the calibration variables. With these calibration variables, I initialize the model to derive the weights. With these weights, I make a weighted combination of their judgments, and then I apply that combination to the self-same calibration variables and score its performance. So here we see the combined score that combines statistical accuracy and informativeness for the equal weight decision maker in red and the performance weighted decision maker in blue. And we see that in almost all cases, the blue is above the red per study. Now, it is not a mathematical theorem that the in-sample validation of performance weighting should be superior to equal weighted combinations. In fact, in what 1, 2, 3, 4, 5 studies or so, the equal weight combination is actually better than performance weighted combinations. But if the performance weighted combination were not massively superior in sample, there would be little point in looking further. But you see, when I apply the performance weighted combination to the same variables used to initialize the model, I do get superior performance. So that's a hopeful sign. But what we would really like is out of sample performance. That is to say, we initialize the model on one set of calibration variables, and then we predict another set of variables and evaluate its performance on this other set of variables. That's called out-of-sample validation. So let's just take a little look at how that works. This is one particular study on geopolitical risk. And in this study, we had actually 18 calibration variables. And so on the horizontal axis here, you see the training set size. And these bars reflect the statistical accuracy of the performance weighted combination in blue and the equal weighted combination in red. And so what you see here is the performance for statistical accuracy over all training sets of a given size. So for example, for training set size 2, we take all pairs of variables, we initialize the model on these pairs of variables, and use that to predict the complementary set called the test set of variables. And what you see here is that for a very small training set, the performance weighting is inferior to the equal weighting with respect to statistical accuracy. That shouldn't really come as a surprise because initializing the model on a small number of calibration variables is just a very bad idea. But you see that as the number of calibration variables increases, two things happen. First of all, the performance weights based on a larger training set are more able to resolve the actual expert performance. And secondly, these weights more closely resemble the weights used in the overall study. And so you see that the gap closes between performance weighting and equal weighting as the training set size increases. And note that this difference is not 7 orders of magnitude, it's a difference of maybe 20%, 10%. If we look down here at the informativeness scores, here we see that the performance weighted decision maker is superior to the equal weighted decision maker in a manner which really doesn't much depend on the training set size. And the reason for this is that performance weight combinations concentrate the weight in a relatively small number of experts who have scored well on informativeness. And so that really isn't affected so much by the training set size. We put these two together and we get this picture. So the combined score is the product of informativeness and statistical accuracy. And so what you see is that as soon as the training set size gets reasonably large, that the out-of-sample penalty for statistical accuracy becomes small, and the advantage of performance weighting in higher informativeness sort of takes over, and the resulting score is then better. So this is the long and short of structured expert judgment. What we want to do is to preserve the statistical accuracy while increasing the informativeness. And we have made these pictures for all 49 of our studies. Here they all are. And I'm not going to go through this in detail, but suffice to say, where you see here this dashed black outline, it means that performance weight looks worse than equal weighting as the training set size gets large. That happens in about 1/6 of the studies. When there's a red border like this, it means that the performance weighted decision maker is actually equal to the best expert. That means that the best expert is getting weight 1, and that happens in about a fourth of the studies. But as you look at these pictures, what you really want to look at is the amount of blue towards the right-hand side of each of these little graphs. So what we want to see is that blue is dominating on the right-hand side. And you see that's sort of overwhelmingly the case. However, if we want to put all this information together in one graphic, we select a certain particular training set size. And we're going to set the training set size equal to 80% of all of the calibration variables. And then we get just one number per study. And per study, we can compare the ratio of the performance-weighted combined score with the equal-weighted combined score. And we see this picture. So in 43 of the 49 studies, the combined score of the performance weight is greater than that of the equal weight. Now, if there were really no difference between performance weighting and equal weighting, the probability should be 1/2 that this fraction is bigger than 1. And if that were the case, the probability of seeing a picture like this, or at least as extreme as this, is in the order of 3 times 10 to the minus 8. So the notion that performance weighting is indistinguishable from equal weighting out of sample is just soundly rejected. Now, since this combination is the product of statistical accuracy and informativeness, we can factor this ratio into 2 separate ratios, the ratio for statistical accuracy and the ratio for informativeness. And here we see the picture that we anticipated a few slides ago. Namely, there is a small out-of-sample penalty for statistical accuracy on the order of 20%, and there is a sizable advantage in informativeness, a gain in informativeness. So it's the product of these terms that yield the picture here. Okay, so that's the story for out-of-sample validation. We now move on to something called the random expert hypothesis. So the researchers who tend to favor a performance blind combination of experts will tend to say or reason somewhat as follows. Well, yes, you can have these performance metrics and you can measure expert performances, but are these differences that you measure real? Wouldn't it be the case that the differences in performance scores among the experts are just the result of random stressors and random fluctuations at the time of the elicitation? I should say at the time of the elicitation of the calibration variables. And these differences then will not persist into the variables of interest or into further assessments of these experts. So these performance differences are not persistent properties of the expert. That's the rationale behind performance blind combinations. Well, with our data, we can test that idea. So to illustrate the idea of this test, we simply consider 3 experts and 3 calibration variables. And in our original panel, we can score statistical accuracy, say, and we can score the average statistical accuracy over the whole panel, or the maximum statistical accuracy over the whole panel, and so forth. Now, the random expert hypothesis says, well, look, this orange expert here, number 1, he may have just gotten lucky in the sense that he read an article yesterday in which the calibration variables happened to be described, so he had a very good familiarity. He could give highly informative and accurate assessments because he just read about them the day before. The blue expert, number 2, just had bad luck because the calibration variables happened just to miss all of the areas of his expertise, so he could not give informative and accurate assessments. Over here, the purple expert, he also had bad luck because he got severe indigestion during the elicitation exercise, and he was very much distracted. And it's these random stressors that explain the differences between the expert performance, according to the random expert hypothesis. So we're going to test that. And we can test that as follows. We make a new panel consisting of random rearrangements of their assessments. So our new random expert number 1 gets the bad luck from the blue expert for the first variable, he gets the good luck from the second expert for the second variable, and he gets the stomach indigestion from the third expert for the third variable. And now we score this panel with our performance metrics and see how it does. And we can repeat this many, many times, and we will build up a distribution for these scores that is generated by this random reallocation of assessments over the experts, or if you will, randomly redistributing the stressors over the expert panel. And the random expert hypothesis says that the score in the original panel should look like it was drawn from the distribution that is generated by the scrambled panels. So to be more precise, if the random expert hypothesis is true, then the performance metrics in the original panel should realize a percentile in the scrambled panel, which in the scrambled panel distribution that is uniform on 0, 1. So what does that mean? Well, it means, for example, that the original panel score for, say, average statistical accuracy over the whole panel, that number has a probability 1/2 of being above the median in the scrambled panels and a probability 1/2 of being below the median. It has a probability of 1/4 being above the 75th percentile, and so on and so on. That's what the random expert hypothesis predicts. So if we just look at 49 uniform random variables and we plot them relative to the value 1/2, so half of them statistically are above 1/2, half of them statistically are below 1/2. And as you look at this picture, statistically, there should be just as much blue above the line 1/2 as below. That's the picture we should see if the random expert hypothesis is true. So what do we see in fact? Oh, wow, that's a little different. So we're showing here now 3 performance metrics, namely the average statistical accuracy over the original panel, the standard deviation of the statistical accuracy in the original panel, and the maximum statistical accuracy in the original panel. And here we have the studies on the horizontal, and we are plotting the percentile in the scrambled distributions that is realized by our original panel for these scoring variables. And what you see is that that percentile overwhelmingly concentrates towards the top of the distribution. Not always, but in most cases. In fact, if we do a little statistics, we can show that the expected number of cases in which the random expert hypothesis would be falsely rejected is about 1/10. So that means, roughly, in 1/10 of the studies, the random expert hypothesis may actually be true. But if we do some simple statistics, in this case, we can show that if the random expert hypothesis were true, the probability of seeing pictures like this or more severe than this is on the order 10 to the minus 12. So this is an obliteration of the random expert hypothesis. It's simply not the case that the differences in expert performance can be explained by random stressors at the time of the elicitation. Okay, now we move on to the last subject, prediction. The scoring variables that we used, you may have noticed, reward statistical accuracy. That's roughly the ability to catch the true value in the appropriate interquantile intervals, and informativeness, which is roughly having narrow confidence bands. Of course, the precise definitions are a lot more detailed than that, but that's for the intuition. Now, there is nothing in those scoring variables that rewards the proximity of the median to the true value. That's not something we score for. So if it turns out to be the case that the performance-weighted combinations yield medians that are better predictors than what we might otherwise get with equal weighting, for example. That's an unintended benefit of the performance weighting, or as we sometimes say, a co-benefit. So to score this, we're going to look at the median deviation per forecast. So that is defined as the forecast minus the realization divided by the realization in absolute value. So we have to divide by the realization in order to make this number scale invariant. So some variables are in milligrams, some variables maybe in light years and whatever. So we want to remove the scale dependency, so we have to divide it out in this way. However, if we do that, the realization can sometimes be zero, and this ratio goes south. So what we really have to do is look at ratios of this median deviation between different forecasters. And that's what we're going to do. We're going to compare two such forecasters. EWQ simply takes the experts' medians and averages them. This is sometimes called quantile averaging. That's why there's a Q here. So even though we have elicited the distributions from the experts, we're not going to use that. We're just going to take their medians and average them. Now, you may realize that the average of the medians is not the median of the average, and that's going to be a pain point here in this forecasting method if we look into more detail. But this is what most people do. This is sort of what you see in the most publications that claim to be doing expert judgment. They just ask experts, give me your best number, and they average them. The alternative is called PWI, and this I indicates that there is a certain flavor of performance weighting that's being chosen here, and I'm not going to go into that here. That's all in the supporting documentation. But what we do is the following. We take an optimized performance weighted combination of the experts' distributions, and then we take the median of that combined distribution. Now we want to compare the median deviations variable-wise for these two forecasting methods. And this is the picture we get. Okay, so here you see the value 1. So if this line is above 1, it means that this ratio is above 1, which means that the equal weight forecaster is further away from the realization than the PWI forecaster. If this is below 1, it means conversely that PWI is further than the equal weight combination. And you see this picture has a strong majority of the lines, the blue lines, are above the value 1. So the probability of seeing a picture like this or more extreme, if there was no difference between these two forecasters, that's on the order of 4 times 10 to the minus 4. So the result isn't as powerful as in the other cases, but it's still plenty powerful. And the reason is that this is a performance variable which is not folded into the performance weighting. It's a co-benefit. So if we look here at these two lines, this green line denotes 10, and the red line here denotes 1/10. So every forecast which is above this green line is a case in which the equal weighting forecast was at least 10 times as far from the realization as the performance weighted forecast. Down here, if it's below this red line, it means that the performance weighted forecast was at least 10 times as far as the equal weighted forecast. And you see that 72 of these lines are above the green and 24 are below the red. So again, a very strong validation of the forecasting advantage that you get by quantifying uncertainty and combining experts with performance-based weightings. All right, so we come to the end. Validation in 4 respects has shown that performance weighting is superior to equal weighting, that is in sample, out of sample, showing that the differences in experts are persistent outside the elicitation context, and finally showing that performance weighting enables you to give better point predictions than equal weighting. So with that, we come to the end of this little presentation. There is a list of references here at the end, and I'm going to sign off, and I hope you will consult supporting literature, and thanks for watching.